peak. The kVp is what accelerates electrons and forces them through the X-ray tube. During an X-ray exposure, the cathode is negatively charged and the anode is positively charged. This difference in charge is called the tube potential or potential difference. We measure the tube potential in units of kilovolts. That's why this technical factor is called the kilovoltage peak. The kVp describes the maximum voltage difference between the cathode and anode during the X-ray exposure. This voltage difference is very important because this is what forces the electrons to move across the X-ray tube. The electrons at the cathode are negatively charged. The anode is positively charged. Since opposites attract, the negatively charged electrons are drawn across the X-ray tube and collide with the positively charged anode. Without the kilovoltage applied to the X-ray tube, the electrons would not move and no X-ray production would take place. Changes in kVp have important effects on just about everything. Changes in kVp affect the beam quality, that's the energy, the beam quantity, that's the intensity or number of photons. It also affects the patient dose, and it affects the receptor exposure. When we increase the kVp, this creates a larger voltage difference across the X-ray tube. This causes the electrons to move more quickly, which then gives them more energy and produces a higher energy X-ray beam. When we decrease the kVp, this creates a smaller voltage difference across the tube, and therefore the electrons move more slowly through the X-ray tube. They have less energy, and the X-ray beam has less energy. kVp is the controlling factor for the energy of the X-ray beam, but it also has a significant influence on the quantity or intensity of the X-ray beam. This is primarily because higher kVp causes a higher percentage of electron energy to be converted into X-ray photons. Remember, only about 1% of electron energy in the tube is actually converted into X-rays. Increasing the kVp makes X-ray production more efficient, and more electron energy gets converted into X-rays. This assumes, though, that only the kVp is changing. We're using a fixed technique that is not AEC, and no other variables are changing. kVp is unique for this reason. It is the only prime exposure factor that can change the energy of the X-ray beam. No other variable can do that. The MA cannot change the energy of the X-ray beam, the exposure time does not change the energy of the X-ray beam, and the distance, or SID, does not change the energy of the X-ray beam. Only the kVp controls the maximum energy of the X-ray beam. The mathematical relationship between kVp and the X-ray beam energy is actually very simple. The kVp is mathematically equal to the maximum beam energy. So in this example, if the kVp is set to 100, the maximum energy photons in the beam are going to be 100 keV. Not all photons in the beam will have 100 keV, but some will. keV is an acronym that stands for kilo electron volts, and that's just the unit of measure for quantifying the energy of X-ray photons. Changes in kVp also influence the patient dose. Increasing the kVp increases the dose to the patient. This is because increasing kVp creates more X-ray photons, which means more photons are striking the patient. Obviously, the reverse is going to be true. If we decrease the kVp, this decreases the patient dose. This again assumes that only the kVp is changing. We're using a fixed technique, not AEC, and no other variables are changing. This relationship can be confusing. Doesn't increasing kVp increase penetration through the patient? Yes, actually, that's correct. Increasing kVp increases the number of photons passing through the patient, and it increases the number of photons absorbed in the patient. This happens because increasing kVp increases both the energy and intensity of the beam. kVp also affects the receptor exposure. That's the quantity of photons striking the image receptor. If we increase the kVp, this increases the receptor exposure. This is an effect of the increased beam intensity, and because increased energy results in more penetration through the patients. As with all these relationships, the opposite should also be understood as true. Decreasing the kVp decreases the exposure to the receptor. This is because fewer photons are created and fewer photons will penetrate through the patient. The relationship between kVp and receptor exposure is actually defined by the 15% rule. As an example, if we increase kVp